Okay, and we'll begin. It's week 5, Monday, week 5, and so next week, week 6, is our absolute last is our last week in the class. Our final exam is scheduled for week 6, Wednesday, and I'm kind of tossing this idea around. I don't know if it's going to happen. I would need kind of like almost near unanimous approval from you, the students. So, I'm just because it's summer, I'm going to be covering new content today, new content on Wednesday, and new content on week 6, Monday. The problem is I'm going to cover brand new content on week 6, Monday, and then your final exam is week 6, Wednesday, which only gives you like a very short amount of time to kind of absorb the material from Monday to Wednesday. And so I'm tossing around a couple ideas. One is to move Monday's lecture to Friday of this week. All right, and so you would have a lecture Monday, Wednesday, Friday of this week, and then that will give you a few extra days to kind of study from Friday to Wednesday. Okay, so that's one possibility. Another possibility is to move the final exam from Wednesday of 6th week to Friday of 6th week. Okay, I think my preference would be to move Monday's lecture to Friday. Okay, but then but again, I would kind of changing schedules and stuff on the fly during the quarter is usually kind of frowned upon unless like nearly all the students agree to this, just because the administration really doesn't like me kind of changing things like that. And so if we can't get a full agreeal on some of these things, then everything will just kind of remain as is. Monday's lecture will remain Monday, and the final exam will remain on Wednesday. But what I think what I'll do is I'll put a vote on Campus Wire, and I think my initial vote will be kind of, do you want me to move Monday's lecture to Friday so that you'll have at least the weekend and a few extra days. The length of the course will still remain the same, ending on 6th week Wednesday, but at least the content will have been prepared a little bit presented earlier and give you a little kind of extra time to kind of learn it and whatnot. So I'll probably put that, and then if that's a fail, then I'll put the other proposal up, which is move the final from Wednesday to Friday. And if both of those fail, then the schedule will just remain as is. Okay. So make sure you kind of check your Campus Wire. I'll also put an announcement in CCLE. So yeah, the final will be 4 p.m. to 5:50 p.m. Regardless, either on Wednesday or again. So I hope this makes sense. My first proposal will be to move Monday's lecture to Friday of this week. Okay, and I'll need everybody to kind of vote in by like Wednesday night or something. And then and if that passes, then we'll do that, and I'll present Monday's stuff on Friday, and then the final exam will be Wednesday at 4 to 5:50, just kind of the original plan. And then if that vote fails, then I'll put up a second vote, which will be, do you want to move the final from Wednesday to Friday? And then if that vote fails, then everything will just remain as is. Okay, does that kind of make sense? Okay, so I'll put the first vote up this probably tonight, which is, do you want to move next Monday's lecture to Friday of this week? Okay, and I mean, some of you guys just watch on video, so it doesn't really matter, but I was just thinking, man, it's a little bit rough to see something and then be tested on it 2 days later. So, and then we have a question. It says, "Hi, Professor. Will our final homework 5 be due before or after the final?" The final homework I will make due after the final, but I will say that doing the homework will be a good way to study for the final, okay? So if that makes sense. So I will make it due after the final, probably like Friday or Saturday of week 6, and but completing homework 5, or at least working through homework 5, I think will be useful as far as your studies go. Okay. The final exam, I haven't decided whether I'm going to do it on Gradescope or whatnot. The final exam is going to be done. So everything I've kind of tried to set up to be a little bit asynchronous, but the final exam will be synchronous, which means, you know, I apologize. Some of you live in different time zones, and so it might mean you have to kind of be up in the middle of the night just for the final exam. But that's going to be the kind of the one thing where it'll be like a synchronous. Everybody has to kind of be signed in for the final. And that's so that will be the one thing that's synchronous. Okay. And yeah, okay, let's all right, let's go ahead and get started here. Today we're talking root finding methods. Okay, and so root finding methods falls under this kind of category of numeric methods, which include root finding methods, and also we'll look at numeric optimization, at least some of the basics of numeric optimization. And basically, a numeric method is, you know, a technique, some kind of method or an algorithm or something, and the whole point is to get an estimate or an approximation to some kind of difficult math problem. A lot of times numeric methods are iterative, and they take advantage of kind of the computer's ability to do calculations very quickly, you know, as opposed to, you know, interpreting kind of symbolic logic and stuff, right? So, so a lot of times we'll use a numeric method when there's some kind of problem that doesn't have an exact or analytic solution, right? You might have something that's very difficult to get analytically, okay? Or you might have something where the exact solution does exist in theory, but, you know, doing the real calculation might be computationally intractable, meaning it's going to kind of take this really long time, or is really complicated to compute the exact answer. Okay, and so these numeric methods, they take advantage of basically the strengths of the computer, right? So here's an example, right? So the PDF of the normal distribution is this, right? This is the standard normal, 1 over root 2 pi e to the negative x squared over 2. This part, e to the negative something squared, everybody should recognize as something that's going to give a normal distribution shape. Okay, so if you are a stats major, you know, if you have the normal PDF memorized, great. But if you don't, what you need to recognize is that e to the negative something squared is going to give you that normal distribution shape. This part up here, 1 over square root 2 pi, is basically a normalizing constant, so that the whole thing integrates to 1. And it's just kind of, you know, like a lot of other remarkable things in math is that, you know, despite having e over here, you know, pi shows up over here, and there's like this, you know, interesting relationship between those two transcendental numbers. Okay, but anyway, this is the standard normal distribution, and the CDF, the cumulative distribution function, right? Which, you know, we get by typing in p norm. You know, we would do this integral, right? The integral from -infinity to whatever z-score you're looking up, and you want to know, you know, what's the area of z equal to 1? What's the area of z equal to 1.96 and stuff like that? This is known as the CDF of the normal distribution. And there's no closed form solution for this. I think you guys learned that somewhere along the way, right? Like in 100B, did you learn that there's no closed form solution for the normal CDF? Maybe, okay, maybe not. But anyway, so if we want to get some value for this, you know, you go onto the computer and you type in P norm and you get basically a value for the CDF. But the truth is that's not the exact value, okay? It's an approximation, all right? It's an approximation. It's calculated. There's this paper that was written on calculating basically the CDF of the normal distribution. And it's an approximation. It's an approximation that's accurate to 16 decimal places. And as far as, and that's good enough for the computer, because the computer, as far as floating point numbers, is really only accurate to 16 decimal places anyway. So and so having a numeric method that gives us an approximation that's accurate to 16 decimal places is good enough for us, okay? But it's not the exact value, right? If you wanted the exact value, you'd have to compute this integral, but we don't have a closed form solution for it. So that's quite difficult. So what we're using is an approximation that's accurate to, you know, 16 decimal places, which is a lot, but you know, it's far from being the true value, right? Like if you said, I only have pi up to 16 decimal places, you know, that's not, you know, we have pi calculated out to like 1 billion decimal places. You know, how useful is that? I don't know, but you know, these things are only accurate to a certain value, right? And so we have to also keep in mind basically floating point arithmetic and the limitations of how accurate you can get with floating point arithmetic, because that's going to be a hard limit as far as any of our root finding or just any numeric method, is that you're certainly not going to be more accurate than, you know, 16 decimal places or, you know, 52 bits. Okay. So the first class is of numeric methods is root finding methods, which is basically find where the function is equal to 0, right? So you have some kind of function, right? And you put in x and it outputs some real number, right? So this is a one-dimensional function that, you know, maps from the real number line to somewhere else on the real number line, okay? And a root is going to be where f of x is equal to 0. So basically, if you were to graph this, it's just where the graph crosses the x-axis, right? And so let's take a look, right? So for example, how do we find the roots of a quadratic function, right? So you have some kind of parabola, and you want to find where are the roots. You know, we can find it using the quadratic formula, right? So this is a root finding method, you know, to find the roots of a parabola, you know, in the form ax squared plus bx plus c, you have negative b plus or minus the square root of b squared minus 4ac over 2a, right? And this will give you kind of the two roots. And that's what we have, right? So if you have an analytic solution, so this is a general rule of thumb. If you can get the analytic solution, use the analytic solution, right? But there will be instances where the analytic solution is difficult to obtain, right? And in those cases, that's when you might consider using a numeric method. So I'm going to be using some references here to the textbook, Introduction to Scientific Programming Simulation Using R. You should have access to that. All right, so the first root finding method is known as fixed point iteration, okay? And so a fixed point is where the function of x is equal to x. So, right, if you have some function g, a fixed point is where g of x is equal to x. And graphically, a fixed point will be where the function crosses the line y equal to x, right? And so one thing about fixed points is that if you keep plugging in the function, right, g of x you're going to get back x. So that means g of x is going to be x, and g of g of x will also be x, right? If x is a fixed point of the function g. All right. Some functions have what we call attractive fixed points. Attractive fixed points. Okay. And that an attractive fixed point is that if you have a is an attractive fixed point, then any kind of value x that's quote unquote close enough to a, and we don't have a formal definition for that right now, but basically if you start off at x and you apply the function g to x, and then you take the function of that result, so you get g of x, and then you apply the same function g to that same function, to that result, and you keep doing that over and over and over again, it will converge to a, which is the attractive fixed point of g. Okay, not all fixed points are attractive, and not all functions, not all functions have a fixed point, and not all fixed points are attractive fixed points. But if you do have an attractive fixed point, that means you can start off with some value, keep plugging it into the function, and plug that result into the function, and it will converge to the attractive fixed point. Okay, here's a little bit more of a formal definition of an attractive fixed point. Don't worry about that. It's just for those of you who like a little bit more formality in these definitions, right? So an example of an attractive fixed point is the square root function. Okay, so the square root function has a fixed point at x equal to 1. So here, let me see. Let me just pull up the Windows calculator here. And I think, you can try this out on whatever calculator you want, right? You just start off with just some arbitrary number here, right? And I'm going to, so this is, what is this? 87,548,632,541. And we will take the square root of that. Okay, the square root of that is 295,886 point something. The square root of that, whoops. The square root of that is 543. The square root of that is 23.32. The square root of that is 4.829. The square root of that is 2.197. The square root of that is 1.48. If I take the square root of that, I get 1.217. The square root of that is 1.10. And if I keep taking the square root, I'm going to get values that are closer and closer to 1.0, right? So now I have 1.00003, 1.00001, 1.0000007, and so on and so forth. And I can keep taking the square root, and we're going to get values closer and closer and closer to 0. So as I continue taking the square root, applying the square root function, that result, whatever it is, will converge to 1, right? And I can start off at, a really small number like 0.0002. I take the square root of that, and you can see it gets closer and closer to 1 as well. Okay, so I get 0.9999999 something, and eventually it will converge to 1 as well. Right? Is that okay as an example of a fixed point? You just keep applying the function, whatever it is, and eventually it converges to a fixed point. Okay, so basically, to find an attractive fixed point, okay, is you start at some value, and then you compute, you apply g to that function, and you're going to get the next value, x1, and then you apply, and you repeat that. You just keep applying the function over and over and over again. And if the function does have an attractive fixed point, and if you have a starting point that's, quote, good enough, then eventually, if you keep doing this, you will reach the fixed point, okay? And usually, you don't want to keep doing this forever. So you're going to just kind of say that the difference between the current value and the previous value, so the xn and the previous value, when that difference is less than some epsilon, okay, or some tolerance level, then that's when you'll stop. So you might say, let's just choose 10 to the negative 6, right? And so when the difference between the current iteration and the previous iteration is less than 10 to the negative 6, we'll say, all right, we've reached something that looks like convergence, and we'll go ahead and stop. Okay, so again, here is the example of applying the fixed point iteration to the square root function. Okay, so I start off at 10. Okay, and so what this illustration is this blue line is the square root function. Here's 10. We say, what's the square root of 10? Okay, the square root of 10 is 3.16. Okay, and what we're going to do is we're going to find where 3.16 intersects with the line y equal to x. And then so at 3.16, we're going to use this as our next iteration, right? So at the next iteration, we start off at 3.16. We go to our function. We say, what's the function at 3.16? The function at 3.16 is 1.77. Okay, so we're going to come over to the line, say, all right, here's where here's where x is 1.77. And so we'll plug that in. And we say, okay, well, what is the square root of 1.77? The square root of 1.77 is 1.33. What's the square root of 1.33? 1.33 is 1.15, right? And so we keep applying. So if we apply the square root to this at y equals x, the next iteration will be at 1.15. And if I do this and I keep applying this, after around 15 iterations, we're at 1.0007, okay? And you can see we'll eventually converge. It might take to converge completely at 1.0, would take infinite number of iterations, but we can probably get something very close to 1.0 after, some finite number of iterations here, okay? Okay, so that is fixed point iteration, and that will find an attractive fixed point of a function if we assume there is an attractive fixed point to begin with. But again, we started off this lecture saying we want to do root finding methods. We want to find the roots of a function, okay? This is not going to find the root. The root of a function is where the function is equal to 0. And this is only finding fixed points. So how are we going to use fixed point iteration for root finding, okay? Well, what we can do is we can say, you know what, we want to find the roots of some function f of x. Okay, we have some function f of x and we want to find the roots of f of x. So what we're going to try to do is we're going to try to find another function g of x. And we will define g of x in such a way that when g of x is equal to x, right, there's a relationship between g of x and f of x. When we find the fixed point of g of x, so that when g of x is equal to x, f of x is going to equal 0. Okay, so here's one example, right? We can just say let g of x equal to x minus f of x. Okay. And if we say, if we define g of x as basically x minus f of x, then when f of x is equal to 0, that's going to happen if and only if g of x is equal to x, right? So this is an example of defining. So we start at, we want to find the roots of f of x, and we're going to define basically a helper function or a sister function or something, some kind of related function g of x, so that when g of x is equal to x, that means f of x is equal to 0, right? And this is one example, right? And there's going to be lots of ways you can define g of x. And some of these ways of defining g of x will have attractive fixed points, okay? So with this, we can find the roots of f of x by finding the fixed points of g of x, right? There's going to be lots of ways to do this, and some of these are going to be better than others. Does this make sense? Does this slide make sense as far as defining some function g of x, so that when we find the roots of g of x, we're going to find find the fixed points of g of x, we end up finding the roots of f of x. All right, let me go ahead and give you the first view quiz answer for today. Week 5, Monday, the first view quiz answer is going to be D as in dog, D as in dog. Okay, so let's say this is an example from the textbook scientific programming using R. It's linked in the syllabus. It's also linked in this slide. And if you're connected to the UCLA VPN, you should be able to download it for free. But anyway, this is an example from the textbook. We want to find the solution to this. We want to find the roots of this function, log of x minus e to the negative x. Okay, so what we're going to do is we're going to try to find some function g of x so that when g of x is equal to x, that means f of x is equal to 0. So I'm going to start off and we're going to say, all right, well, here's f of x equal to 0. And then let's try to solve for x, right? So what I'm going to do is I'm going to add e to the negative x to both sides. And then I'm going to raise both sides to e, right? E to the log x is x, and e to the negative x is going to be this over here. Okay, and so when so we're going to set g of x equal to this, and basically when this thing is equal to x, then that's also going to be a solution to when log of x minus e to the negative x is equal to 0, right? So if we're able to find the fixed points of this function, that will also be a root of this function over here. Okay, so so here, this is my implementation of fixed point iteration. Here's my function. G is e to the e of negative x, right? So exp of negative x, this is my function over here. And then I'm just going to start off at 10. Okay, we're going to call this x old, and we're going to say the new value, x new, is going to be g of x old. All right. We'll start off at 0 iterations. I'm going to say my tolerance is 10 to the negative 8. So we're going to keep running until the difference between the old and the new is going to be less than 10 to the negative 8. Right? And we're going to say we're going to run a loop. While this is true, while the absolute value of the difference between the new and the old is greater than my tolerance here, then take my current new value, set it equal to my old value, and then calculate g of basically this old value, set it equal to the new value, all right? And then let's add 1 to the number of iterations. Is that all right? Does that make sense? As far as fixed point iteration, all we're doing is we're just applying g to the old value to get your new value, and you're just going to kind of repeat this over and over and over again. All right. And so now sometimes these algorithms don't always converge. So it's always good to basically have an exit that basically says if the number of iterations reaches, say, over 10,000 or something, or 1,000 or whatever it is, that it's just going to quit as well. And that way it doesn't run forever. All right. And so this is the result that it gets. Okay. My value after however many iterations gives me 1.3098. If I plug that into the function, log of f of, basically f of x, basically log of x minus e to the negative that, okay, we get something that is on the order of 10 to the negative 10. So that is, that's good. That's approximately 0. So we're happy with that. And it says it took us 19 iterations to get there. Okay, maybe 19 or 20 iterations. Okay. And so, yeah, basically, mathematically, this works out, right? If we assume that there is some kind of attractive fixed point, then we can show that basically as n goes to infinity, then the limit of g of this thing is going to be g of this thing, as basically we're making this assumption that xn is going to converge to some value. And so there you go. A is a fixed point. Okay, that is, if the fixed point iteration method converges, then it does converge to a fixed point. But does fixed point iteration always converge? And the answer is no, it doesn't always converge. Okay, the convergence of a fixed point relies on the existence of an attractive fixed point. If it doesn't have an attractive fixed point, it might not necessarily converge. Okay, And so again, not all functions have fixed points, and not all fixed points are attractive. So we are not, so it's not guaranteed to converge. Okay, and sometimes some fixed points are what we call repelling fixed points. Okay, meaning you can start close to the fixed point, but then when you plug it into the function, it ends up diverging or being repelled by the fixed point. Okay, so one condition depends on the derivative of that function g of x. So the derivative g prime of x at the fixed point, and if the absolute value of g of the derivative of g at that fixed point a is less than 1, if the absolute value of the derivative is less than 1, then a is going to be attractive. Okay, so what if I wrote the function this way? Okay, so here f of x is log of x minus e to the negative x. We set that equal to 0. And then what we're going to do is we're going to say, well, let's just add x to both sides. If I add x to both sides, okay, then when g of x, if we define this thing as g of x, when this thing is equal to x, then that means that's going to be where this, which is f of x, is equal to 0. So when g of x, if we define g of x as log of x minus e to the negative x plus x, when that thing's equal to x, then we have a root of f of x. Okay, but if we try to run this, okay, and if I say, break after 1,000 iterations, okay, so it's the same code as before, but here I put in a limit that prevents it from running forever. What we end up getting is it ended up running basically for 1,000 iterations and it didn't converge. And when we try to plug this value into the function, we get something that's very much not 0. Okay, so that's something you have to watch out for, right? There's going to be lots of ways you can try to write some function g of x, okay, so that when g of x equals to x, that will be when f of x equals 0, but they're not always going to work out. Okay, any questions on fixed point iteration and using it to find a root of f of x? All right, let's talk about Newton-Raphson method. Okay, Newton-Raphson method. So fixed point iteration is a simple thing. Once you have the function g of x, all you do is just keep plugging the value into g of x. But the convergence is often kind of pretty slow. Okay, pretty slow. So one thing that works generally a lot faster is the Newton-Raphson method, okay? And the idea behind Newton-Raphson method is you take a tangent line to the function, and the tangent line is basically a linear approximation of the function at that point. And the hope is that, when you're getting close to a root, if you just zoom in right where that function crosses 0, the line, y equals 0, right when you find right where that function crosses 0, if you zoom in really close, it might look kind of like a straight line. Okay, and so so basically, what we're going to try to do is we're going to try to find we're going to use the tangent line to figure out, where should we go next, right? So we're going to say, let this function f have a root a, right? So we're going to say the function f, whatever it is, crosses the, the x-axis at point A. We have to also assume that the function has a derivative, okay? And the derivative is continuous, otherwise it's going to break, right? And we're going to say, let's start off with some initial guess, x0, right? And we're going to take the derivative of f at x0, okay? And we're going to say, okay, what's the equation of the tangent line at f of x0, right? And so basically, that's going to be f of x0 plus f prime of x0, the derivative, the slope there, times x minus x0, right? So, I don't know if you guys remember back to your algebra days, this is basically a kind of like point slope form of the function. And again, basically, the reason this works is if you do a Taylor series expansion for f of x at the point x0, right? The Taylor series expansion is basically this, f at x0, f prime of at x0 times x minus x0, and then f double prime times x minus x0 squared, and so on and so forth. Basically, we're just taking the first two terms, and then we're throwing everything else away, okay? So we're gonna, basically we're doing this. The Taylor series expansion basically, says you can get the, expand the whole function at that point, right? And okay, and so basically we're going to apply this, and we're going to use that tangent line to figure out what the next value we should use in the in this iterative method. Okay, so maybe a picture will help us, right? So here's just a very simple line. Okay, x squared minus 3. Okay, x squared minus 3. When you plug in the number 10, is going to give us 97. Okay, and we're basically asking, where does x squared minus 3 cross have a root, right? Okay, and so this is going to have a root at the square root of 3. But we're going to just start off with the initial value 10. Okay, that gives me this point 97, right? And what's the slope? Okay, at 10, right? So the slope here is basically 2x. Okay, so the slope is 20, and we say, all right, let's draw a line tangent here, and we're going to trace this tangent line, and it goes down and it crosses basically the x-axis, like right around here. Okay, a little higher than 5, I think like 5.15 or something like that. Okay, and so we say, okay, let's plug in 5.15. All right, so we plug in 5.15. 5.15 squared is something like 25 minus 3, a little bit higher than that, 20 something here. Okay, and we say, okay, what's the tangent line there? So we take the tangent line, and tangent line at that point takes me down to here, 2 point something, 2.86, and we say, okay, let's plug in 2.86 to the thing, right? And we get find the tangent line, and that takes me down to here. And we can see if we kind of keep tracing this, this is going to get me closer and closer to the square root of 3. All right, so at my next iteration, I'm at 1.95, and so on and so forth. Okay, so how did we get this value, right? How did I end up at 5.15 here? Okay, all right, so what we can do is we can say, all right, the definition of the slope is rise over run, right? So this is, back in algebra, we say the slope is the rise over the run. Okay, and so we say, well, at x equal to 10, x0 is equal to 10, my rise is 97, the slope is f prime at x0, right? 2x, right? The derivative of x squared minus 3 is 2x, the slope is 20. Okay, and so basically, if we say slope is equal to rise over run, okay, I'm going to just kind of rearrange the terms to say run is equal to rise divided by slope, right? And so if I do the run is 97 divided by 20, this part, this length here is 4.85. So 10 minus 4.85 is going to give me 5.15. Okay. How do we, and so, plugging that in, the tangent line will cross the axis, okay, at 10 minus 4.85. So it crosses at 5.15, and that's going to be my next iteration. So x1, the value that we're going to use in the next iteration, is our current value x0 minus f of x0 divided by f prime of x0. And this is the Newton-Raphson method. Okay, so we just generalize this rather than using iteration 0 and iteration 1. We're going to say that the next iteration x at time n plus 1 is our current value x at time n minus f of f at x at time n divided by f prime at x at time n. Okay. And that's the Newton-Raphson method. Are there any questions there? That's how this works here. So again, I think the pictures work best in that you start off someplace, you take the tangent line and you follow it, okay? So this is the Newton-Raphson method, okay? And so in your homework this week, you're gonna be kind of basically recreating some of these graphs here. You're gonna write a function to do Newton-Raphson method and also try to, create these graphs. Okay, so here's the algorithm. Just start at some initial value x0, and you repeat this process, okay? Where you just, at each iteration, you calculate the next value as the current value minus f at the current value divided by f prime at the current value, okay? And again, you're gonna stop. We're just looking for the root, and you can just stop when the value f at xn is close enough to 0, right? So when you say, okay, when this function gives me a value very close to 0, then we're going to call that a root, okay? We're going to call that a root. So you have some pre-specified tolerance level, and we're going to just stop when the function gives me something that's close enough to 0. Okay, so let's go ahead and apply this to this function, right? So here's our function. This is the one that we used in the previous example. We've got log x minus e to the negative x. We have to figure out the derivative. So f prime, so the derivative of log x is 1 over x. The derivative of e to the negative x is e to the negative x times -1. And so that becomes plus e to the negative x here. So we have this, and we're going to kind of code this up, okay? So our f is log x minus e to the negative x, and then f prime is 1 over x plus e to the negative x. All right, and so I'm just start off at some arbitrary value 2, okay? But we can plug, a lot of different values. And we start off with iterations equal to 0. My tolerance level is going to be 10 to the negative 8. And again, we're going to keep going until the value at f of x is less than this. Okay, so as long as the value of f of x is greater than this tolerance level, we will keep running the iteration. Okay, so I've got, so we're going to say, here's my current value. Current value is x. We're going to subtract off x minus f of x divided by f prime of x. Again, that's basically the algorithm, x minus f divided by f prime, okay? And we're going to update that to be our next current value of x, okay? And then we'll just calculate the next iteration. I hope that code makes sense as far as the Newton-Raphson method. Okay, and we let it run, and basically, it converges just after 4 iterations. After 4 iterations, it arrives at this number, 1.3098. And we say, is that right? We plug in 1.3098 and we find out, oh yeah, f at that value is something very close to 0, right? We said if it's less than 10 to the negative 8, we're going to call that close enough to 0. And it's at 10 to the negative 9. So, so it gave us something very good. And it only took us 4 iterations to reach that value. You can check this math. The Newton-Raphson method will converge if it converges. So if it converges to a root. But does it always converge? And the answer is it doesn't always converge, okay? If f is well behaved, meaning, okay, first of all, the function the derivative at the root cannot be equal to 0. Okay, so that would cause problems, right? So if you have a function that basically like kisses the x-axis, right? So at the root. So if your root is at a and basically your function, quote, kisses. So you can think of like the function y equal x squared. Y equal to x squared has a root there at x equal to 0, but the derivative at x equal to 0 is also 0, right? So that's going to cause problems. So first of all, the derivative at the root can't be 0, and the second derivative has to be finite and continuous at a. Okay. Then you can start off with some value that's close enough to a, and it will converge. Okay. So Newton-Raphson method converges quadratically, but it's not always going to converge. Okay. So, and sometimes just because of some properties of the function and your starting point, you can end up getting stuck in basically these things that don't converge. And so in your homework this week, you're going to code up the Newton-Raphson method. And I also have provided different functions where you're going to apply the Newton-Raphson method to try to find the roots. Okay. But some of the examples in your homework intentionally will not converge, or intentionally, basically intentionally will put you in some kind of situation where the function does not converge. And sometimes you'll have the same function, but based on the starting point, the path it takes to find the root or not converge is going to be different. And so you'll see kind of the interplay between the function and your starting value, your initial value, and see whether that converges to some root or not. Okay. And basically, you don't know if it's going to converge or not until you try it out. And that's basically how a lot of these numeric methods work, right? We're using the reason why we're using the numeric method in the first place is because we couldn't figure out the analytic method, right? And so a lot of times you're going to apply a numeric method and you're not quite sure if it's going to converge until you let it run. And when it does converge, it may not even be like a function can have multiple roots, and maybe you're looking for a particular one, and it's possible that you let this function run or this algorithm run, and it converges to a root, but it's not the root that you're looking for. Okay, so here's a bunch of things where the Newton-Raphson method can fail, right? So if the derivative is equal to 0 for at any some value, right? So you got a bunch of iterations, and if x at time n, if the derivative there is equal to 0, then the tangent line becomes horizontal and it's not going to cross the x-axis, right? And so that will fail, right? If this just happens, this is going to fail. Okay. And even if it's not equal to 0, let's just say it ends up being really small, like 1/1,000,000. Okay. Let's say the derivative at some location is not exactly 0, but it's very small, 1/1,000,000. And in that case, where it crosses the x-axis could be like way off, right? Like if the derivative is like 1/1,000,000, then it's not flat, so it eventually does cross the x-axis, but the slope is almost flat, and so where it crosses the x-axis could be something like -2 million, right? That could happen. Okay. Convergence can depend on the initial guess. If the starting value is too far from the root, the method might not converge, or it could converge to a different root. Sometimes, depending on the function, the iterative locations can end up oscillating back and forth, right? And you end up getting stuck in a cycle. And you'll see an example of this in your homework. Okay. If the second derivative is infinite or undefined at the root, it can also cause non-convergence, right? And in some non-ideal scenarios, right, where you have this, okay, the Newton-Raphson might still converge, but the convergence might end up being like really, really, really slow, okay? I think we've got an example animation here. So here's basically a function that we have there. Here's another. Let's reset this. Okay, so you can see. So here's a thing. The function's root is over here, right? The root is over here. This is where it crosses 0. but you get this spot right here where the derivative is very, well, it becomes flat. Okay, you do have a derivative equal to 0 at some location around here, right? And so as it's running, okay, it gets kind of stuck here, and it ends up kind of oscillating back and forth, and it comes over here, and this thing shoots it over here, and you can see. So finally over here, it converges until it required. So you can see, because the derivative over here ends up being in the other direction, it ends up getting shot back over here, right? So stuff like this could happen. Okay. This is an example where I think it finds it here. Okay, that works fine. Here's one where it kind of oscillates and doesn't converge. Okay, it just gets farther and farther away. Okay, so it starts off, and every time it kind of just ends up oscillating and going farther away. Right. So these are, so after a long time, it doesn't converge. It just goes off to infinity. This is a good example here. So again, it starts off, but each time it calculates, it just keeps going farther and farther away. Okay, so you have all sorts of reasons why it might not converge. Okay, but when it does converge, it's pretty great. Okay. Let's do another one, secant method. So I'm just showing you a whole bunch of these methods, and you know, some of these things, definitely several of these, or a few of these, will show up on the final exam. You know, I'll ask you to kind of do some of these things probably manually here to make sure you understand how it works. Luckily for you, the exam's open book and open notes, so you know, you can look through your notes here. Okay. Newton-Raphson method is very much desirable because it converges quickly, but one of the downsides is that you have to compute the derivative of the Newton-Raphson method analytically. Okay, and if the derivative is really difficult to figure out analytically, then one substitute is the secant method. Okay, and so the secant method is very much like the Newton-Raphson method, except you're not going to calculate the derivative. You're going to use a secant line as basically an approximation to the tangent line. Okay, so the secant method requires two initial guesses. You're going to start off with an x0 and an x1. Okay, and it doesn't matter if x0 or x1 is larger or smaller than a or whatever. Okay, but you're going to draw a line that connects those points, x0 and f of x0 to the point x1 and f of x1. And that's your secant line, and you're going to just kind of continue that secant line until it crosses the x-axis, right? And then where it crosses the x-axis is going to be the next value that we use, right? So here's a picture of what I'm talking about, all right? So rather than needing to figure out the slope and the tangent line at x equal to 10, I'm going to start off with two initial points. We're going to start off with x0 equal to 10 and x1 equal to 8. Okay, and so here's x0 equal to 10, x1 equal to 8, and I'm going to draw a secant line. Okay, I'm going to draw a line that connects this point to this point, and we've traced this line all the way down to here. Okay, and this is going to be my next point. Okay, and so the next iteration is going to use this point and x1, which is 8. All right, so we'd say, all right, what is this value? This value is, I don't know what this is, 4 point something. Okay, we take this point and this dot. All right, this forms my secant line. Okay, and so I draw a line going from there through there, and I trace it down to here. Okay, and now we use this point, and I draw a secant line through there, and we just keep going, right? And then so the next one ends up here, and then the next one we go, and we just kind of iterate through there, right? So these are all secant lines. All right, and so the first line starts off at x0 equal to 10, and the point is 97 because my function is x squared minus 3. And then the next point is 8. So we have 8 squared minus 3 is 61, right? And so the slope of the line that connects these two things is the change in y. So it changed from 97 to 61. Okay, so that's a change in what is that, 36, right? 97 minus 61 is 36. Okay, and then we say, all right, what's the change in x? Well, the x went from 10 to 8. Okay, so it changed 36 and it changed to 2. So 36 over 2 gives me a slope of 18. Okay, which is a little bit different from the tangent line has a slope of 20. This tangent line, or not the tangent line, the secant line has a slope of 18. Okay, and then so we say, okay, well, what's this point right here? Okay, well, the equation that passes through this, okay, it goes through the point 61, and 18 times x minus 8. So we're going to find where this equation is equal to 0, and it's equal to 0 at the point 4.611, right? So we solve for where y minus f of x1 times m times x minus x1 is equal to 0. We get 4.611. Okay, and so I'm going to use that, all right, as my next guess. The next value x2 is going to be 4.611, and we continue on, right? So in general, the slope of the secant line is going to be the change in f of x1 minus f of x0 divided by the change in x, x1 minus x0. And the equation of the secant line in point slope form is going to be this, which means your next value, okay, the next value that we're going to use is going to be this, right? So I'm kind of skipping over a little bit of the math here, but you can say, all right, so in point slope form, we have, y minus f at x1 times the slope m times x minus x1. And so, so we have this, and we plug in our value for the slope right here. Okay, and then we're going to try to solve for where this thing is equal to 0. So I'm going to replace y equal to 0, and we're going to say, all right, where is the next value going to equal? What's x2 going to equal, right? So what is x2? So here I'm going to multiply both sides by this inverse. So we have to assume that this is not going to not dividing by 0, right? So we multiply both sides by this inverse here, and then I'm going to add x1 to both sides. And so the next value that we're going to use, x2, is going to be x1 minus f of x1 times basically the inverse of the slope of the secant line. Okay, and this is actually quite similar if you look back to Newton-Raphson method. If you look at Newton-Raphson method, it's basically the current value x1, your current value times f at the current value times 1 over the inverse of the slope. Okay, and basically we're going to say basically you have the current value minus f at the current value times the inverse of the slope. Okay, except the slope is given by, the secant line, the change in y over the change in x. And that's going to be your next value, x2. Okay, so more generally, x at the next time iteration is going to be x at your current iteration minus f at x at your current iteration times the inverse of the slope of the secant line. The slope of the secant line is the change in f divided by the change in x. Okay, basically f at your current iteration minus f at your previous iteration, and x at your current iteration minus x at your previous iteration. So the inverse of the slope there. Okay, and again, it says, if xn and xn plus 1 are close to each other, then the slope is pretty much is approximately equal to this. And this is basically like a finite difference approximation of the derivative. All right, let me go ahead and give you your next view quiz answer. The next view quiz answer is the letter C, C as in cat, C as in cat, C as in cat is your second view quiz answer. Today's second view quiz answer is C as in cat, okay? So here's the secant method written out as an algorithm. You need two initial values, okay? Two initial values, x0 and x1, but you no longer need to have the analytic derivative figured out. So that's a nice thing. Okay. Convergence properties of the secant method are similar to the convergence properties of the Newton-Raphson method. And just like the Newton-Raphson method, we cannot guarantee convergence, okay? And the main trade-offs is we no longer need to figure out f prime, but we do lose some speed, and we do have to figure out two initial points, x0 and x1. All right. We'll cover another root finding method. So today, just a whole bunch of these root finding methods. So the last one is the bisection method. Okay, bisection method is one of the simplest numeric methods, and it almost always works. Okay, but the disadvantage is convergence is slow. Okay, and it's gonna it works by doing root bracketing. Okay, so first it says, all right, here's an interval. Here's some place on the number line. And we know there's got to be a root somewhere in here, okay? And we're going to just basically, we just keep shrinking this interval in half. And we keep choosing, where the root has to lie, right? So in bisection method, we keep shrinking that interval in half. And so basically, this is going to work as long as your function is continuous, okay? As long as f is a continuous function and you have a root in the interval, okay? All right, and we're going to say you have x on the left and x on the right, okay? So you have the bounds of your interval is xl for x on the left and xr for x on the right. And you've got a root if xl is negative and xr is positive, okay? Or vice versa, if xl is positive and xr is negative, then there's got to be a root there, right? So if one side is positive and another side is negative, there's got to be a root. If one side is negative and the other side is positive, there has to be a root, okay? And so we can just check to see if there is a root within the interval. If xl, so we just say f of xl times f of xr, that number has to be negative, right? As long as the product of f of xl and f of xr is negative, that means they've got opposite signs, and that means there has to be a root between between xl and xr, okay? And what we're going to do is we're going to split that interval in half, and we're going to try to figure out which side we're going to keep. And so we keep having the interval until the width of the interval is less than some tolerance E. Okay, so we have some tolerance value, epsilon, and we're going to keep shrinking the interval until the width of our interval is less than some tolerance level E, epsilon. Okay, so this is how it's going to work. Okay, you start with an x on the left and x on the right, so where they have opposite signs, and you know there has to be at least one root in there. If x on the left and if f is a continuous function, right? If f is a continuous function and one side is negative and one side is positive, there has to be at least a root there, right? So, so what we're going to do is, well, we'll check for convergence first. If the width of our interval is less than our tolerance level, we can just stop. Okay, we can just stop. Okay. Otherwise, we'll continue. We're going to calculate the midpoint. We're going to find the midpoint of f of x and of the interval xl and xr. And then if that midpoint happens to equal 0, well, great, you found the root, okay? But generally it probably won't. And then so if it doesn't equal 0, then what you're going to do is you're going to say, okay, is the midpoint negative or positive, right? Or does the midpoint have the same or opposite sign of f of xl, right? So you're going to just take the left interval and you're going to say, does it have an opposite sign of f of xl, right? So you're going to do find f of xm multiplied by f of xl. If that thing is negative, then that means that the left-hand side and the midpoint have opposite signs. And then the midpoint can become the, can now become the right side of the interval, okay? So if that's the case, then we're going to say the right-hand side is now, the new right-hand side is going to be the midpoint that we calculated, right? You have the left-hand side, the right-hand side, you calculate the midpoint. If the left and the midpoint have opposite signs, we're going to just take the midpoint and set this to be the right-hand side. And then we'll keep searching for the root inside here, okay? But if the left-hand side and the midpoint don't have opposite signs, then you're going to assign the midpoint to be the new left-hand side, okay? And so now you keep the original right-hand side, and now you're searching for the root between the left-hand side, the midpoint and the right-hand side. Okay, so this is basically the heart of the bisection method. You calculate the midpoint, and you're going to see what is the sign of the midpoint. Do I keep the left-hand side in the midpoint, or do I keep the right-hand side in the midpoint? Okay, and then after you do that, start over again, and you keep doing this. You keep having it until the left and right-hand side is less than some tolerance level of epsilon, or you happen to crash into the midpoint, and crash into a root at the midpoint. Okay, so at every iteration, the left-hand side and the right-hand side will always contain a root, okay? And assuming we start here, the algorithm is guaranteed to converge, okay? And basically the rare error amount is going to be reduced in half at each iteration, right? If you have multiple roots in there, it's just going to end up converging to one of them, okay? It's going to just end up converging to one of them. Right, and if we stop where this, then we know that XL and XR are both within some epsilon of the root, and probably you will just take the next midpoint and report that as the value you find. Okay, so again, we're going to just use the same function that we've been using, log x minus e to the negative x, and we're going to try to find the root. Okay, so we know the root is something like 1.3098 or something, I don't forget what it was, right? So here we're going to say, all right, we know that the root has to lie in between 1 and 2, right? So we might have had to find these by guess and check, but we're going to just set the left-hand boundary to be 1 and the right-hand boundary to be 2. We're going to set my tolerance to be 10 to the negative 8. We can find f at the left-hand side. We find f at the right-hand side. And do f at the left-hand side and f at the right-hand side, do they have opposite signs? Yes. Okay. And so this is how the bisection algorithm works. Okay, so we're going to say while the right-hand side minus the left-hand side is greater than some tolerance value, just keep repeating these things, right? So we're going to start off with iterations equal to 0, right? So first we find the midpoint, which is the left-hand side plus the right-hand side over 2. We calculate f at the midpoint. Okay, and if f at the midpoint is equal to 0, we're going to just do an all equal. If f at the midpoint is close enough to 0, we will quit. Okay, and we'll just take f at the midpoint. Otherwise, we're going to ask if f at the left-hand side, this has already been calculated, times f at the midpoint, okay, is less than 0. Okay, and if that's the case, then take the midpoint and assign it to XR. Okay. Otherwise, take the midpoint and assign it to XL. All right. And, oh, you know what? I'm missing something important here. we assign xm to xr and xm to xl, but then you have to kind of, you take f of xm, and that also should get assigned to f of xr, f of xl. Okay, so we would assign xm to xr, and then I would also need to calculate, I think, recalculate that. Okay, but anyway, we run this and it converges. Okay, so this is kind of what our picture looks like. We start off at 1 and 2, and we divide this in half. All right, so we know, so the root is here. Okay, we divide this in half and we say, all right, which side are we going to keep? At 1.5, we're going to throw away this side. We're going to keep the 1.5 becomes our new right-hand side. And then we're going to divide this thing in half. Okay, we divide that in half, and we're going to throw away this side. Okay, because we're going to keep it so, you know, we're having this interval here, and we're always throwing away the side that doesn't contain the root. Okay, we divide this thing in half, and it gives me over here. We divide this thing in half, and apparently this is like really close to the root, but it's still positive, so we're going to throw away that side. So we're going to divide this in half, and we throw away that. Okay, we divide that in half, and we throw away that. Okay, and it just kind of keeps going over and over and over again. Right? Does that make sense as far as how this bisection method is working? Okay.
Sorry, I have a question.
Yeah.
So like, is it important for us to at first guess two possible roots so that their their product is less than 0, or like it's not very important?
Well, you do need to do a little bit of probably trial and error to make sure that you have a left-hand side and a right-hand side that have opposite signs.
Okay.
Okay.
Got it. Yeah.
So, you know, so you do need to start off where left-hand side and right-hand side have opposite signs. Okay.
Got it. Thank you.
Okay, and so the kind of, as far as root finding methods and kind of production settings, use a bit of a combination of these things. We use root bracketing to get kind of close to a root, and once we do, we switch over to Newton-Raphson or Secant method to you know, accelerate even faster, right? So root bracketing will kind of get us close, and then, but you know, the convergence, once it gets really small, is a little bit slow. So once you get close, you switch over to kind of Newton-Raphson and Secant method, because those things work well as long as you're like close to the root, you know, where, you know, a linear approximation works pretty well, right? And so this so that's kind of a best of both worlds approach. Okay, the order of convergence, you know, we talk about the error between the actual root and our approximation at the nth iteration, right? So we have our approximation at the nth iteration, and so the error is the difference between the actual value and our approximation. And we're going to say the order of convergence is when kind of the next iteration, okay, the next iteration can be defined as basically the error at your current iteration raised to some power p, right? Some power p. And so basically, if it converges, you know, at a second order, then that means at next iteration, you know, it's going to be, you know, whatever order you have raised to the pth power. Okay. We don't have to worry too much about this, but basically higher orders of p mean it converges much faster. Okay, so if we think about, say, the bisection method, right? The bisection method has a order of convergence of 1, okay? Since the error is reduced by a factor of 2 with each iteration, right? So right? If we think about how the bisection method works, it just kind of halves it at every single time. And so you can think, okay, well, what's my current value? So we can't take my current error and then raise it to some power. Okay, so you take the next value is basically just half of your current error, right? So you're not raising the amount of error. It has this, right? Under the Newton-Raphson method has quadratic convergence. We're not going to try to show this, but it can be shown that under, kind of these ideal conditions, the next iteration, the amount of error at the next iteration is going to be kind of your current amount of error squared. Okay, which means it's going to be a lot smaller. So that's going to have quadratic convergence. Okay, whereas the secant method, again, we're not going to be showing any of this stuff, okay, or deriving this, but the secant method has an order of convergence of around 1.6, okay, which is the golden ratio. Okay, so these are just kind of like neat little, I guess, tidbits or facts. And so, the Newton-Raphson and secant method are preferred methods because they converge faster. Okay, whereas the bisection method, it only has linear convergence. It's a little bit slower, but it's also a safe method, right? The bisection method is guaranteed to converge. Okay, whereas Newton-Raphson is not guaranteed to converge. And so, again, the best of both worlds approach says use bisection method to get us kind of close, and then when we're pretty close, and when we're pretty close, we can switch over to Newton-Raphson to converge even faster. All right, so those are all of our root finding methods. Okay, those are we covered 4 different root finding methods, and you've got some homework problems covering that. The other thing we'll take a look at is going to be today we'll look at derivative approximation. Okay, so in the Newton-Raphson method, we had to calculate the derivative analytically, and sometimes calculating the derivative analytically is can be hard. Okay, so anyway, this is the Newton-Raphson method, and again, you need to figure out f prime. Okay. And so sometimes you're able to calculate the derivative analytically, and you can write a function that does this, right? So if we have this function, this is what we did earlier. I'm just copying some of the slides earlier. We can take the derivative of this, and calculating the analytic derivative is not hard because these are just kind of simple functions, right? And this works. Okay, this works. We can just do log of x is 1 over x. E to the negative x is e to the negative x, and so on and so forth, right? And so here's this, and we can get the tangent lines, okay? But sometimes finding the derivative can be difficult, or finding the derivative, the analytic derivative could just be this really complicated thing that requires a whole bunch of stuff, okay? And so in those cases, we might want to do a numeric approximation to the derivative, right? And this is all where we're just taking advantage of the computer's ability to compute numbers. And so rather than calculating the analytic derivative, we're going to just approximate the derivative. And if you can approximate the derivative, then you can basically do Newton-Raphson or some other method and do something pretty good, right? So if we think about what is the definition of the derivative is this, right? As h goes to 0, you're looking for the difference between f of a plus h minus f of a divided by h, right? So f prime, the derivative at a, is equal to this limit. Right? So you guys all learned this in your single variable calculus. This is your definition of the derivative. And so what we're going to do is we're going to just approximate this thing. Okay, we're not going to take the limit as h goes to 0, but we're just going to use a really small value of h, right? We're just plug in like h equals 10 to the negative 5 or some small value of h, and we say, oh, okay, if we plug in a small value of h, I'm going to get some approximate value here. right? And hopefully that will be good enough. So you have some function. Okay, here's the function is log of x minus e to the negative x, right? And so if we, we can actually calculate f prime, but here I'm going to just approximate it. Okay, so if I approximate this, I'm going to just say, all right, let's take h is 10 to the negative 6, just a tiny value of h. Okay, and then so we'll say, all right, what is f of x plus h? We're going to just do log of x plus h minus e to the negative x plus h, right? I'm just adding h to x. I'm going to plug that in, and we get f of x plus h, right? So then we say, what's the difference of f of x plus h minus f of x divided by h? And so this is going to be my approximation of the derivative, right? And so we can say, well, okay, how close is the approximate with the actual value, right? So we're going to say, all right, I want to see 12 digits here, and the approximation is 0.206737923, okay? And the actual f prime, at 5, if I plug in 5, I get 0.206737994, right? So it's accurate up to 1, 2, 3, 4, 5, 6, 7 digits, and at the 8th digit, it's off, right? 1, 2, 3, 4, 5, 6, 7 digits are the same, and the 8th digit is off by a little. So my approximate derivative, I would say, is pretty good. And if you wanted to get even more accurate, you can change this to something a little bit smaller even. But again, you have to be careful, because depending on the function, you might run into the limits of floating point arithmetic, right? Floating point arithmetic, depending on your function size, is basically only accurate to 52 bits of precision, and it depends on how large the original value is, right? Okay, what if the h that you're adding is negative, right? So you learned about like the right-hand side derivative, and you also learned about like the left-hand side derivative, right? So as h goes to 0 from the right, or as h goes to 0 from the left, you can end up getting slightly different values, right? So over here, I had h being a small positive value, but here I'm going to make h a small negative value, all right? And so what is my value there? Okay, so if I plug that in, okay, I end up getting 0.2067379 and the value 7, right? So both of these things, coming in from the right, coming in from the left, we are very close to the true value, 0.206737994. But if you look at this value, if you look at this part here, 9.4 versus 9.7 and 9.2, in this case, so let me just scroll back a few pages. So here I'm on slide 84. If you look at this, here's the function 5, and the function curves like this. The function curves like this. And so basically, on one hand side, we are coming in from the left, and the slope is too high. And on the other side, we're coming in from the right, and the slope is too low, right? And I think I actually have this. Okay, so the left-hand side approximation is too big, right? So here on the left-hand side, this is exaggerated, but the slope is too steep. And the right-hand side is exaggerated, and the slope is too shallow. And the true value is somewhere in between. Okay, so if there's curvature in the function, the left-hand side and the right-hand side approximation will, differ a little bit. Okay, one side will often be a little bit bigger than the true value, and the other side will be a little bit smaller. And so to kind of correct this issue, one thing we can do is we can kind of look at both the left-hand side and the right-hand side approximations and kind of take an average of the two. Okay, so rather than doing f of x plus h minus that, I'm going to have, here is my h is 10 to the negative 6, and I'm going to do log of x plus h minus e to the negative x plus h. So on one side, I'm going to add h, and on the other side, I'm going to subtract h. Okay. So I add h on one side, and then I subtract h on the other side. And so now I've gone up, 10 to the negative 6 on this side. I've gone down 10 to the negative 6. And so my distance here is 2 times 10 to the negative 6, right? So I'm going to take the difference between f of x on the right-hand side and f of x on the left-hand side, and I'm going to divide by 2 times h, right? So this will be my balanced approximation for the derivative. And if I do that, look how many digits of accuracy I get here, okay? It's 0.20673794698, okay? So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits of accuracy, because the true value is also 0.20673794699. So I've got about 10 digits of accuracy by doing the approximation, a right-hand side and left-hand side, and using both of those values to get an approximation, right? So the balanced approximation is even closer to the true value. All right, so we can do that, and we can just generalize this to basically any function, right? We can generalize our derivative function. So with functions, you can use other functions as arguments, right? So the derivative of f, this is an approximate derivative of f. We're going to say, I need a function, and I need the value of x, and we're going to do some value h, and then we're going to do x minus h for the left and x plus h on the right, and we're going to take the function of the right minus function on the left divided by 2 plus h, right? So this will figure out the derivative of f of any arbitrary function. This is an approximation, okay? And here, if we use this, it's not even necessary to actually calculate the derivative. We can just approximate it, right? This is kind of cool, right? Or am I the only one impressed by this? So here I just say, okay, here's my function. Here's my function, log of x minus e to the negative x, right? And I'm going to say, all right, give me f, the f derivative, which is this function here. Give me the approximate derivative of the function f at 5, okay? And it gives me this 0.20673794698, which we know is pretty accurate. All right, let's try another function. What if I have another function? f2 is x squared, right? So we know analytically what is the derivative of this function. Derivative of this function is 2x, right? So we say, all right, give me the derivative of function f2 at the location 5, right? Okay. And if I ask for 12 digits of accuracy, we say, oh, it's 10.1000000014. So this is, again, this is an approximation, but it's a pretty good one. Okay. And here, all we do is we're just starting off with some function, and we just say, what's the derivative here, right? And again, so we can say, all right, just to illustrate what happens with floating point numbers is you say, well, you know what, how accurate are we, right? So here the amount I'm adding or subtracting is 10 to the negative 6. And we can say, well, will I get more accurate, less accurate if I use bigger, smaller values? So here I'm going to try, okay, well, how close do we get if I use 10 to the negative 5, 10 to the negative 6, 10 to the negative 7, 10 to the negative 8, right? So 10 to the negative 6, I have, well, the true answer is 10. 10 to the negative 5, the true answer is 10, and I get 9.999999996, okay? Here, I have 10.000000000. 10 to the negative 7, I actually have less amount of precision, okay? And at 10 to the negative 8, I even have less. And as I shrink my H, the amount that I'm getting starts getting off and off, right? And if I try to use 10 to the negative 16, it can't even calculate the derivative correctly, right? If I say add H is 10 to the negative 15, my derivative is way off. The true value is 10, and it's giving me an approximation of 8.88, right? This is way off as far as what is the derivative at that value. Okay, and again, what's happening is the with floating point arithmetic, remember, we have to we're calculating x squared, right? So my value is 5, okay, and what we're doing is we're doing 5 plus some number, okay, 5 minus some number and 5 plus some number. And so depending on what your original number is, at 5, how many places do we have, right? So what is kind of the smallest value you can add? And then we're going to have to plug it into the function, and we square it, right? And so if you think about the number and basically how many, as your numbers get bigger, the amount of kind of precision you can have over here decreases, right? You have less precision. So because as the number itself gets bigger, you can only keep like a total number of like decimal places or binary places to begin with. And so we have to adjust what H is depending on what kind of your input X is. As your input X gets bigger and bigger, you're going to have to adjust H to also be bigger. And it's a good idea to kind of play around with it. But you know, 10 to the negative 6, 10 to the negative 5 is probably a good choice for a lot of in a lot of situations here. All right. Why don't we call it a day here? So we'll end there. Let me give you your last view quiz answer. Today's last view quiz answer is the letter A. A as in apple. A as in apple is going to be your last view quiz answer. Okay, so we'll go ahead and end there. I'm going to put a poll up on Gradescope, and I'm going to need to get a lot of responses. So please respond, and to see whether or not you guys are okay with moving Monday's lecture to Friday. We'll do that, and then and if you guys are okay with that, I will present. We'll have 3 lectures this week, and then we won't have a lecture on Monday, but we'll have the final exam on Wednesday. And my hope is to just kind of present the material a little bit earlier so you have a little bit more time to study. But again, administration doesn't really like me to just kind of change the course schedule like that too often. So, but if I can justify it and say, you know, the students, we had a vote, the students approved it, and therefore I did it, then they'll be okay with that. So, so be on the lookout for that, and have a good night. Okay, so we'll see you guys on Wednesday, but check out the poll on Gradescope.
Hi, Professor. I have one question.